So we've learned about forces, which are one way to figure out how things behave in a classical system. And if you know all the forces, you can work out what's going to happen in the future. That can be quite complicated though. Simpler ways of working things out involve looking at conserved quantities. And the first one we saw was momentum. Now momentum is always conserved. It only has one form. The only disadvantage is it's a vector, so it has three components. It's got a magnitude and a direction, and so when you write down a conservation of momentum, what you're really writing down is three conservation laws. The conservation of momentum in the x direction, the conservation in the y direction, and the conservation in the z direction, all in one hit. A simpler quantity that only has a scalar quantity is something like a charge, and charge is always conserved, but problems that require us to use the conservation of charge don't turn up that often, except in more exotic situations, so while being completely true and very important, it's not very useful. There's mass. Mass is just a scalar, but it's not always conserved. It's mostly conserved. That said, at non-relativistic speeds and so forth, when you're not worrying about nuclear reactions, mass is effectively conserved. So you can use things like conservation of pens or conservation of stormwater. If a lot of water goes into a drain, you can figure out how fast the water has to be coming out the other end. You can work out traffic flow and so forth using conservation of mass. So that's a good rule of thumb. And we've also learned about conservation of energy. Now, energy is important in lots of everyday situations. It's a scalar, so that's very handy, and it's always conserved, which is great. The only problem is it comes in lots of forms, and so to use it, you have to learn all the different forms of energy and track how energy travels from one to another. And in fact, this tracking of how energy and learning how to use energy is one of the main things that enabled us to change our technology over the last few hundred years from all the millions of years of fairly static technology beforehand. Access to available energy is absolutely critical to our modern life. It is a dominant force in international and domestic politics. And you might ask the question, if energy is conserved, how can that possibly be? And the answer is fairly simple. Energy has a lot of different forms, and some of those are really easy to use, and some of those are basically impossible to use. So for the vast majority of human history, the main energy source that we could access was the energy stored in our own muscles. Or if we're going to get the biology right, more specifically, I guess the bulk of it was stored in the liver in the form of glycogen, or in fat cells in the form of fat. Now, how did that energy get there? Well, that's a long story. Essentially, it came from nuclear reactions in the sun into sunlight, light down in through the sky into plants. Plants converted it into sugars. The sugars were either eaten by animals or by us, and then the animals were eaten by us, and somehow all that got together into our glycogen and fat stores, and we could run, jump, and adjust our environment to our heart's content. And even, of course, once we use that energy, the energy isn't gone, it's just changed form. So what's happened is that chemical potential energy in the chemicals in our body is turned into some kind of useful work and some waste heat. It was actually the unbelievably important discovery that heat was a form of energy that allowed us as a species to go beyond the limits of what could be done with just the chemical energy stored in our own muscles and in the muscles of any animals that we domesticated. Besides perhaps the occasional water wheel, all energy that we were using was coming from us. And this is a huge limitation, even if we were using machines to try and use that energy and do that work as efficiently as possible. So instead, when we discovered that heat was a form of energy, we learned not only that we could put work and create heat, so we could, say, bore out a cannon and make it hot in the process, we also discovered how to do the reverse, which is how to use a fire to make, say, a steam engine and create work and useful energy out of making things hot. When we discovered we could burn things in some way and make them hot and then use that to do work, that's what changed the world. That's how we got from millions of years of very stable technology to suddenly the Industrial Revolution and things changing on an enormous scale. So at a microscopic level, heat energy is really just the kinetic energy of the particles moving around. So if you have, say, a gas of particles and they're all moving around at different velocities, then they each have different kinetic energy, but on average you'll have a certain amount of energy stored in the kinetic energy of that gas, and that's the heat energy ultimately. And the hotter something is, then all these things are bouncing around and they'll have this bigger, hotter distribution of energy. They'll have more energy per particle on average. So in the context of trying to get energy out of our muscles and to do useful things, then normally we think of the work as the important thing. So this is stuff done by the force that our muscles produce. And we think of the heat as a waste byproduct. And indeed, that's often the case. So often when you're trying to use energy, you end up producing some kind of low temperature heat as a result. And if you produce high temperature heat, like if you're building a fire in a steam engine, you can use that to do work. But if you have low temperature heat, then you're basically, that energy is not in a usable form anymore. And there's this whole discipline of physics called thermodynamics where we talk about exactly what the limits are on trying to extract energy out of different sources of heat. So when you talk about using energy, you're really talking about transforming energy from one form to another form, or sometimes from one form to multiple other forms, of which you really only want one of them. And that means that we always have to worry about the efficiency of that process, which is just the fraction of energy that you extracted into the form you wanted, divided by the total amount of energy that you used. So in this case, it would be the work divided by the chemical potential energy that we used.